most prevalent gas that we have in room air? All right, did anybody guess? Did you guess oxygen? Right. Well, oxygen is actually number 2. It's the second most prevalent gas that we have. The first one is nitrogen. Okay. Nitrogen makes up roughly 78%. It's actually a little higher than that. It's closer to 79. 78% nitrogen. Oxygen, about 21%. That's pretty darn close to actually exactly 21%. And the third gas is carbon dioxide, which is always written as less than 1%. Right. And if I remember right, and you can check me on this a little bit later, I believe it is actually 0.03%. Okay. So it's actually quite a bit less than 1%. Right. So those are the 3 gases that make up room air. Now when we breathe in air, we do put a 4th one in here. We have to consider water vapor, because air in the respiratory system is quite humid. Now, there's another gas law we need to consider, and it's called Dalton's law of partial pressures. Dalton's law of partial pressures, and I'm not sure it's in the slides here. Yeah, it's not. All right, Dalton's law of partial pressure says that the pressure total of a system is simply equal to the sum of all the different pressures of the individual gases. And it goes on and on and on for however many gases we have that make up our gas mixture. So room air is a mixture, and it has, we know, nitrogen, and it has oxygen, and it has carbon dioxide, and any other gases that we throw in there that are in trace amounts. Whoops, not the best art in the world. Okay, so what we call these individual gas pressures is we call them their partial pressures, and usually that's just P, N2, PO2, and PCO2, and that's how we write that. All right. Now our total pressure in room air at sea level is 760 millimeters of mercury. And it's got to be the sum of these 3 individual gas pressures. So to give you an idea how this works, let's take a look at a graph. All right. Here are our 3 main gases. 1, 2, and 3. Here are their relative makeups. They used 0.04 instead of 0.03. So you can adjust that number as needed. Here's nitrogen at 78.6 and oxygen at 20.9. So I rounded this, I said 78, 21, and 1. Right. But it sums up to 100%. Okay. What you do now is you take your total pressure, which is 760 millimeters of mercury, and you simply multiply that by these individual percentages. Right, so you take this and you multiply it by these, and that gives you pardon me, the partial pressures. So if I took 78.6% of 760, I would get 597 being the partial pressure of nitrogen in atmospheric air. Nitrogen is the guy we all forget about because it doesn't have a physiological role. It doesn't do anything that I know of for the body tissues, while these 2 gases are plenty important physiologically. So our partial pressure of oxygen is probably the one we want to pay attention to right now. If I took my 21% roughly and multiplied that by 760, I would get 159 millimeters of mercury as my partial pressure of oxygen. Right. And it works out that if I take my 760 and multiply it by my 0.035, which is I think what it really is, I get about 0.3 as my partial pressure for CO2. Right. Now look over here. Right. When I breathe in, these percentages of the gases in alveolar air are quite different than they are out here. Right? Nitrogen's not changed that much. It's mostly just diluted because of what we have with carbon dioxide. All right. Again, oxygen, that drops quite a bit. Right. Oxygen's at 21% in room air, but when we breathe it in the alveolar space, it's at 13.7%. Partially because we're taking that oxygen away all the time, but also mostly because we've diluted it with these two. Okay. This is a fixed volume of gas, and so if you add other gases to your mixture, it's going to effectively reduce the percentage of the ones that were already there. So look at what happens with water vapor. Okay. In inspired air, we hardly have any. It's 0.46. But in alveolar air, it's up to 6%. So that's, what, more than 12 times higher the amount. So there's a big increase in the humidity when we breathe it in. And that's because the respiratory tract is moist and it adds water vapor to the inspired air along the entire thing because the respiratory membrane is moist and has to stay moist. So we really do need to humidify the air to keep that moist, otherwise the respiratory membrane will dry out. All right, carbon dioxide, big jump in carbon dioxide as we go from inspired air to alveolar air. And that is mostly because of the residual volume that you have in your lungs. The residual volume in the lungs is high in CO2. When this air comes in, it mixes with the residual volume that's in the dead space of the lungs. And when it does that, it effectively dilutes the gases that we brought in. We brought in a very small amount of CO2, so it adds a lot of CO2 to that because that's what's in the residual volume. We brought in fresh supplies of oxygen, and we mix that with depleted air that's already been in the lungs in the residual volume, so our percentage of oxygen goes down. Right? So here are some partial pressures that we deal with. Roughly about 14 oxygen, 5.2 carbon dioxide. And this is in the alveolar air. These are not, I'm sorry. I hope I didn't misspeak. I might have. These are not the partial pressures. These are the percentages. Okay, I knew that wasn't right. Now you take that and you multiply it by your total pressure again, which is still 760. And now we get our partial pressures. And so here, that's what we want to pay attention to. So in inspired air, the partial pressure of oxygen is 159, but in the alveolar air, the partial pressure is only 104. Again, because we effectively diluted it. In inspired air, the partial pressure of carbon dioxide is only 0.3, but in alveolar air, it's a whopping 40. It's very, very high. These numbers are important. Okay, these are what we want to pay attention to, and I'll explain why in a second. Okay, so we just explained how we get our partial pressures. Let me back up one slide, or a couple slides here, and make mention of this. Henry's law is another gas law similar to Dalton's law and Boyle's law. Henry's law states that the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the liquid, or at the gas-liquid interface. For all intents and purposes, what this means is that if you increase the pressure of a gas around a gas solution, the gas will dissolve to a greater extent in that solution. It doesn't really have a big physiological significance when it comes to carbon dioxide and oxygen, but it has a really significant role to play with nitrogen. Ordinarily, we don't have a lot of nitrogen dissolved in the blood, but if you take nitrogen, say, with you in a contained air supply like a scuba tank, and you dive down to 20 meters or 40 meters, you're going to double and triple the atmospheric pressure. And when you do that, you're effectively creating a high pressure area around the solution, i.e. your blood. Nitrogen will dissolve to a greater extent in your blood under those circumstances, which isn't a problem. But when you come back up and those pressures decrease, the solubility also decreases, and the nitrogen literally bubbles out of the blood. Your blood, in a way, you can think of it as boiling. Nitrogen pockets form, and that can cause pain, and that's a condition called the bends, and it can cause mental confusion. It's a condition called nitrogen narcosis. And it can cause rupture of blood vessels, and ultimately that was what would be deadly about this disease. So it's a problem that scuba divers have to pay attention to. If you're going to dive at, say, a depth of 20 meters for a certain amount of time, when you come back up, you have to learn your dive table so that you know how long to hesitate at 15 meters and 10 meters and 5 meters, so that you can slowly, gradually vent off the nitrogen so you don't develop the bends. Additionally, Scuba divers are discouraged from flying in an airplane for at least 24 to 48 hours after they've gone scuba diving, because airplanes are only pressurized to about half of an atmosphere. So again, if you go from feeling fine at sea level to riding in an airplane, you can actually develop the bends as a result of the decreased pressure. Now on to partial pressure gradients, which is what we need to talk about next. Okay, in this slide we're listing our two relevant partial pressures that I mentioned to you just a minute ago would be important. In our venous blood, and you can think of venous blood as blood that has passed through tissue spaces. So it's given up its available oxygen to the tissue spaces, and now it's on its way back to the heart and to the lungs to be reoxygenated. So this is our low pressure point. Right? And the alveolar PO2, that's where we've just oxygenated the blood. And so this is our high PO2. And as it says here, the significance of this is it creates a diffusion gradient, 104 to 40, and that effectively drives oxygen from the pulmonary spaces into the tissue capillaries. And I'll just ask you to keep this number tucked away in the back of your mind. It only takes about a quarter of a second for the blood as it flows through the pulmonary capillaries to get oxygenated. The condition for CO2 is just the opposite. We have a high PCO2 after we've passed through the capillary bed, so that's our venous blood, because the metabolic tissues have given up carbon dioxide to the blood. So that is a relatively high number. In the alveolar space where we're venting off CO2, this should be a lower number. And so this is our gradient here, driving CO2 from the blood and the tissue spaces into the alveolar space. Right. Let's go on to the next slide here. So here's a slide I like. This represents the fact that when we breathe air in, it's relatively high in oxygen with a PO2 of 160, relatively low in carbon dioxide with a PO2 of only 0.3. Now we breathe this air in and it mixes with the residual volume. And we've talked about the residual volume before. When it mixes with the residual volume, we increase the amount of CO2 and water vapor that's present in this air. So before we've done any gas exchange, our partial pressures change a little bit. Rather than being at 160, the PO2 is only at 104. And rather than being a paltry 0.3, the PCO2 is 40 in alveolar air. Now we know that the condition we're having here is that the pulmonary arteries are delivering deoxygenated blood into this space. And that's where we're going to have external respiration occur across this respiratory membrane, which consists of the pulmonary capillaries and the type 1 squamous pneumocytes of the alveoli. Okay, so we want to have carbon dioxide leaving the pulmonary capillaries and going into the alveoli. We want to have oxygen coming from the alveolar space into the pulmonary capillaries. Let's look at oxygen first. Okay, we have a PO2 of 104. That is enough to go ahead and cause the oxygen to diffuse into the capillaries, because in the capillaries we currently have a PO2 of only 40. So that's our gradient. This PO2 of 40 that we have in the veins, the systemic veins, yes, the systemic veins, pulmonary artery and pulmonary capillaries, comes from the fact that in the tissue spaces, the tissues are using up the oxygen, lowering the PO2, and here it says less than 40. That number could be anywhere from 0 to 40. By the time we collect all of the blood in the systemic circulation up back to the heart and then send it off to the lungs, on average we wind up having a PO2 of about 40. So there's our gradient. We have an oxygen PO2 of 104 in the alveolar space, and that goes down to the tissue spaces where we have something below 40. So that's obviously a diffusion gradient. All we got to do is get the oxygen to the area and the gases will diffuse. One little hiccup along the way you might notice as the blood comes into the capillary beds in the tissue spaces, its PO2 is not at 104. It's only at 100. So let's explain that. when the blood is coming from the lungs via the pulmonary veins, we actually have a little spot here where some deoxygenated blood in the bronchial veins, oops, that's supposed to be a period, the bronchial veins comes in, and that's deoxygenated blood coming from the lung tissue. So it's not coming from the alveoli and the pulmonary capillaries, but it's coming from the bronchial capillaries, which are delivering, which are taking deoxygenated blood away from the structural components of the lung. It's not a large blood supply compared to the pulmonary veins, so when it enters this deoxygenated blood, it just dilutes the PO2 a little bit, so it drops from 104 to 100. What we'll see, guys, is that that's not significant, the 104 or the 100, or that drop from 160, because hemoglobin is fully saturated at a PO2 of 100, so we don't suffer any functional loss with these drops. When we get to the tissue spaces and the incoming blood in the arterioles has a PO2 of 100, it's going to encounter lower PO2s in the tissue spaces, and oxygen will unload from the hemoglobin and go to the tissues. The tissues, meanwhile, are generating carbon dioxide. So here we expect to see our high PCO2, and we do. A PCO2 here, it says, of greater than 45. Now, there aren't any tricks or anything that's diluting or changing this, so we go back to the lungs. Go back to the heart, and then we're pumped off to the lungs. So coming in to the lungs on the pulmonary arteries, we have a PCO2 of, again, 45. Even with the mixing of residual volume and the humidifying of the inspired air, the PCO2 is still lower than 45. It's at 40. So there's our gradient for CO2. Okay. Let me back up here for just a second and talk about the respiratory membrane. I told you what the respiratory membrane was just a second ago. It was our type 1 pneumocytes. Right, type 1 pneumocytes and the endothelium. The endothelial cells. That's what a respiratory membrane is. It's very, very thin. It's less than a micrometer thick. That's to allow for very rapid gas exchange. If this becomes thickened as a result of disease, like pulmonary fibrosis or pneumonia or cystic fibrosis or even influenza, infiltration of mucus and fluid into that area, then gas exchange is impeded, because gas exchange is a diffusion process. There's a few things I want to remind you of. For gases to diffuse across the membrane, they must be dissolved in the liquid in the liquid surface of the membranes, and that carbon dioxide is much more soluble and quicker to diffuse than is oxygen. And another thing about diffusion is that it's highly dependent on distance. So if I double or triple this distance, I'll effectively cut the rate of diffusion at least in half, and maybe even more. Diffusion drops off precipitously with small increases in distance. So if we increase our respiratory membrane as a result of disease, effectively we become hypoxic. We retain too much carbon dioxide and we don't get enough oxygen. All right, the next concept I want to touch on, before I leave this idea, back here with our partial pressure gradients, there is a short answer on the test where I ask you to describe the partial pressure gradients. So for that, you need to tell me what the partial pressures are in inspired air, what they are in the alveoli and why they're different, and then what happens to the PO2 in the pulmonary veins, why that drops a little bit as a result of mixing with the bronchial veins, and then how we do, so that would be external respiration there, and then internal respiration is what happens in the tissue spaces. So tell me about the PO2 driving oxygen down into the tissues. And then conversely, the reverse, you need to be able to tell me the PCO2s in the tissue spaces and in the alveolar space. And always keep in mind on these two big red arrows here, which are our, sorry, didn't mean to do that, which are our partial pressure gradients. Okay, next concept. Ventilation and perfusion. Perfusion is the degree to which we supply blood to the lungs, and ventilation is the degree to which we move air in and out of the lungs. We need to match these two concepts for efficient pulmonary function. So it says here, changes in PO2 levels in the alveoli cause changes in diameters of the arterioles. So let's just chew on that for a minute. Right. So the PO2 we know is the partial pressure of oxygen in the alveolar space, is what we're talking about here for the alveoli. Pardon me. So our pulmonary capillaries in the arterioles are sensitive to the O2 in the alveolar space, in the concentration. If we have a condition where the alveolar O2 is higher than normal, what does that represent? Why would the alveolar O2 be higher than normal? Well, simply put, it would be because the blood flow is inadequate to extract the oxygen. You're bringing in the oxygen into the alveolar space, presumably to diffuse it into the pulmonary capillaries. If the blood flow is too sluggish, such that the oxygen is kind of hanging there and building out, it's not being building up, it's not being swept away. So what we want to have in that case is we want to have the arterioles dilate. Okay, now this is somewhat contrary, because in the systemic blood vessels, if our O2 concentrations are high, the blood vessels actually constrict and slow down the oxygen delivery to that tissue because it doesn't need it. Here, if the alveolar O2 is high, the arterioles dilate to allow more oxygen to be diffused into the pulmonary capillaries. And just the opposite is true if we experience low alveolar O2. If the oxygen in the alveolar spaces is low, well, that means that the blood flow is actually too rapid and we're sweeping away the oxygen too quickly. So in that case, we constrict the blood flow and allow the oxygen allow the level of oxygenation to equilibrate. Sorry for my senior moment there. When we look at the levels of PCO2, it's not the arterioles that are sensitive to concentration levels of carbon dioxide, but it's the bronchioles. So in this case, where we have alveolar CO2 levels high, well, that means that the ventilation rates are too slow, and we're getting a buildup of CO2 in the alveolar space. So if the alveolar CO2 is high, bronchioles dilate to increase ventilation. When we have alveolar CO2 levels that are low, that means that we're actually ventilating too quickly. We're sweeping the carbon dioxide away too rapidly. So in that case, we constrict the bronchioles a little bit, slow down the ventilation rate, and allow for more exchange of CO2 to come from the blood. So what this boils down to is we're trying to match these two all the time. So if we take a look at this graph, this is where part A, panel A, says ventilation less than perfusion. So something to keep in mind is that we are always in one of these two states. We're never perfectly matched. We're either ventilating under perfusion, that's how you could say ventilation less than perfusion, or we're ventilating over perfusion, both of which are not good. So let's talk about what happens here. If you're ventilating less than perfusion, so think about that. That means we have inadequate gas supply into the alveolar space for a adequate or rapid blood supply. Well, what's going to happen? If the blood is flowing more rapidly than we get oxygen in, then that means we're going to fail to oxygenate our pulmonary capillaries adequately. So if ventilation is less than perfusion, if we're over perfusing, in other words, that's another way of saying it. Okay, and that's what they're saying here: increased perfusion or decreased ventilation. Well, in that case, you're going to get inadequate oxygenation of the blood. Okay. If ventilation is less than perfusion, you get inadequate oxygenation of the blood. And likewise, we're going to get a buildup of CO2. So think about that. What did the previous slides just tell us was going to happen? If you're getting inadequate oxygenation because you're getting excessive perfusion, then the thing to do is go ahead and constrict your arterioles. And that is exactly what happens. We constrict the arterioles a little bit, slow down the blood supply, and allow it to oxygenate properly. Okay. If we go over here and take a look at what happens, if your ventilation is greater than perfusion, so now we're getting too much air passing over too little blood, is a way to think of that. Well, we don't really see a problem with the oxygenation in this case. The oxygenation is full because we're bringing in plenty of air for the amount of blood flow that we have. If anything, the only problem we have here is that we're wasting blood flow. Well, yeah, we maybe have fully saturated the available blood in half the amount of time, and so it's wasting some of that time. The real issue here is that if we're ventilating too quickly, that means that we're actually venting off too much CO2. As a result of the blood supply going kind of sluggish through the pulmonary capillaries, we wind up giving off too much CO2, and then our PCO2 levels drop way low. This has consequences because this will change the pH of the blood. As we'll see, the pH of the blood is very dependent on CO2 levels, and so if we vent off too much CO2, that actually causes the blood to become alkaline. It rises. Remember, blood pH should be 7.35 to 7.45. In this condition, which would be caused by hyperventilation, right, where you're ventilating beyond what you should ordinarily, you can actually develop what's called a respiratory alkalosis. And oxygenation of the blood will actually be impaired because of poor hemoglobin function. All right, so if we're in a condition where ventilation is greater than perfusion, we can do two things. Remember, again, increased oxygen. Well, we actually want to speed up the oxygen supply and let it flow through more quickly. So we go ahead and dilate the pulmonary arterioles to allow the blood flow to increase. And that'll allow more oxygen. Well, it'll allow more efficient flow, so we'll get more blood flow through. So hopefully we'll still get full oxygenation, but we won't be wasting that blood flow. And then let's take a look at what happens with the perfusion and ventilation from the CO2 aspect. So let's go back over to panel A. If ventilation is less than perfusion, so we're underventilating, well, what we need to do there is, well, we're going to see an increase of CO2 because the CO2 is building up in the alveolar space. So that increase of CO2 is going to cause bronchodilation and will increase ventilation. In this case here, if we're ventilating greater than perfusion, what we're going to have to do here is that's going to cause the CO2 to go down, and that's actually going to cause bronchoconstriction and give a little bit more time for CO2 to exchange. All right, internal respiration. Internal respiration. This is capillary gas exchange in the tissues. Again, it's partial pressure gradient driven. It says reverse compared to external respiration. Well, let's take a look at that here. We're back to this chart. All that means is that, look, in external respiration, we want to drive oxygen from the air into the blood. And in internal respiration, we want to drive oxygen from the blood into the tissues. The way in which we transport oxygen and carbon dioxide in the blood is markedly different. Oxygen is almost exclusively carried on hemoglobin, reversibly bound to the iron ion in the center of the heme. You can bind 4 molecules of oxygen to every hemoglobin. And then interestingly, you have 250 million molecules of hemoglobin in every red blood cell, and you have trillions of red blood cells. So that tells you that you can bind 1 billion oxygen molecules per red blood cell. Pretty staggering. Very little oxygen is actually dissolved in the plasma itself. We've talked, pardon me. Goodness, losing my voice. We've talked a little bit about hemoglobin in its states before. When hemoglobin binds to oxygen, we call it oxyhemoglobin. When hemoglobin loses the oxygen is replaced by a hydrogen atom, and that is called reduced hemoglobin. Reduced hemoglobin is another way of referring to deoxyhemoglobin. So in the lungs, we take hemoglobin, bind it to oxygen, and form oxyhemoglobin. In the tissue spaces, we take oxyhemoglobin, remove the oxygen, and form deoxyhemoglobin, or reduced hemoglobin, thereby liberating the all-important oxygen to the tissues. We know that taking oxygen and putting it onto hemoglobin is called loading. And if we take the oxygen back off, we call that unloading. And that's what hemoglobin does reversibly. It says here, facilitated by changes in shape in hemoglobin. What that means is that, remember, that the heme chains, the heme rings, which are in the base, which are in the middle of every heme, goodness gracious, the heme group and its iron are in the middle of a globin chain. When heme is bound by oxygen, the globin chain actually goes through what's called a tautomeric shift. It just changes its shape a little bit. And what it says here is, as oxygen binds, it actually increases its affinity for more oxygen. So when the first oxygen binds, it causes the next one to bind more easily, so on and so forth. And the reverse is also true. As oxygen is released, it makes it easier for oxygen to give up more oxygen. As oxygen is released, it makes it easier for hemoglobin to give up more oxygen. As we'll see, hemoglobin is not usually in a state of full saturation. It's somewhere in between. It's usually partially saturated. We will talk about these factors right here that affect hemoglobin loading and unloading now. We'll go through this in sequence. However, what we need to take a look at is the hemoglobin dissociation curve. Right? Hemoglobin dissociation curve. That's what we're going to look at right now. And here it is. Okay, so we'll spend some time on this. What the hemoglobin dissociation curve tells you is it's basically an index that allows you to look up some information. The x-axis, if you look down here, contains PO2s. And the y-axis is percent saturation of hemoglobin. Here's a little diagram on the left-hand side showing you what that means. Here's a hemoglobin cartoon with no oxygen bound, 1, 2, 3, and 4. So this would, if this were to take and graphically depict all of the hemoglobin in the body, then if all of it was bound to 1, we'd be 25% saturated. If all of it was bound to 2, we'd be 50%, so on and so forth. Now that isn't really exactly what happens, but it gets at the idea. So what you can do is you can look at any PO2 and see that at that partial pressure, how much of the hemoglobin in the body we'd expect to actually be saturated with, or to what degree would we expect it to be saturated with oxygen? How much of the hemoglobin would we expect to be saturated? So out of this comes a basic tenet, and that is that hemoglobin saturation is dependent on partial pressures. That's the primary driving force for hemoglobin saturation. So here they've picked two relative numbers that we've discussed before. In alveolar air, after we've diluted with the carbon dioxide that's present in the water vapor, we're left with a PO2 in the lungs of about 100, and then that drops down, or 104, and it drops down to 100 in the pulmonary veins. And so here we have the value of 100 written on here. Well, I'm sorry, it's right here. So at a PO2 of 100, which is what we would encounter right here, okay, and here even, okay, at this region here, on our way off to the tissue spaces and having left the lungs, okay, we would encounter a PO2 of 100. And what this tells us is if we follow this line up here, we see that on our graph, that tells us that pretty much hemoglobin is fully saturated. Now, in truth, it's not 100. It's about 98%. But we're saturated as much as you can be. And you can see that at this point, the graph has pretty much become a horizontal line, which means even if we drove this up to 160, like it was in inspired air, we'd get virtually no gain in hemoglobin saturation, because after all, it's already at 98%. Okay. Now this blood travels through the systemic circulation, goes to the capillary beds where it gives up oxygen to the tissues. Well, why does it do that? Because in the tissues, let's say the PO2 down here was 40, right? That was a relative number we used. Let's look at our chart. If you come to a PO2 of 40 and follow that up right here, you'll see that the hemoglobin saturation is roughly 75%. which means that we dropped from here to there, and we gave up 25% of the available oxygen. Now this is interesting for a couple of reasons. One, we tend to think of blood delivering oxygen, all of its oxygen, to tissue cells. Well, that's not what this tells us. This tells us that as the blood flows through here and encounters a PO2 of 40, it only gives up 25% of its available oxygen, meaning it has a reservoir or a reserve of 75% of its available oxygen still. So from that reason, we say that, or for that reason, we say that hemoglobin really can function as an oxygen reserve or reservoir. Right? Let's think about the target tissues here for a second. Skeletal muscle at rest doesn't use a lot of oxygen. So as blood is flowing through this capillary bed of skeletal muscle at rest, it may only encounter a PO2 of 60, okay, or 55. Let's just say it's 40. And we've given up 25% of our available oxygen. Now we travel down to another capillary bed, and in this capillary bed we encounter a muscle that's actively metabolizing. So here's a question for you. What do you expect the PO2 to be in active skeletal muscle compared to resting skeletal muscle? What do you think the PO2 in active skeletal muscle would be compared to the PO2 in resting skeletal muscle? Given that the resting skeletal muscle has a PO2 of 40, what do you think the PO2 would be in, say, an actively contracting muscle? All right, well, the answer is lower, quite a bit lower, because the actively contracting muscle is using its available oxygen, and so it creates a very low PO2. If you're stressing a skeletal muscle maximally, you might drive that PO2 down to below 5. Well, let's look at this chart. I'm going to estimate here. If that's 10, then this would be about 5. Okay. If I had actively metabolizing skeletal muscle, I might drop here to 5. Well, if we follow that up and then over, that's going to give me an O2 saturation of around 5%, because maybe a little bit lower. Well, now the available hemoglobin has given up 95% of its available oxygen. So it's pretty much spent at this point. It doesn't have anything left to give. Well, what this does, guys, is this ensures, without any fancy modes of regulation, it ensures that the most actively metabolic tissues get the most oxygen delivered. Okay? The most metabolically active tissues have the lowest PO2s, and our hemoglobin dissociation curve shows us that the lowest PO2s are going to cause the greatest unloading, and we're going to deliver oxygen to those tissues. So it's really a pretty slick mechanism. So that's the standard curve. The way you use the curve is you pretty much pick a PO2, and then you look up on the chart what percent saturation you would expect the hemoglobin to have at that particular PO2. And if that were the whole story, it'd be interesting enough. But what we can do is we can shift this curve. We can shift the curve to the right. It's a rightward shift. Or we can shift the curve to the left. It's a leftward shift. And what I mean by that is we don't distort the shape of the curve too much, although it does change a little bit, but we don't really distort the shape of the curve. We just slide it along the x-axis. So a rightward shift of the curve might look like this. That's a rightward shift. There are environmental factors that would shift a curve to the right. Now what I want you to understand about a shift of the curve to the right is that it favors unloading. Okay? Shifting the curve to the right favors unloading. Now what do I mean by that? Well, let's pick this tissue PO2 of 40 that we might encounter in our standard curve shown in blue, we said, look, we only give off about 25% of our available oxygen here. But if I shift this curve to the right for some reason, look what happens at that same 40. All right, come over here. We'll say that's maybe 38. So rather than unloading only 25%, we've unloaded 62% of our available hemoglobin. So that's what I mean by it favors unloading. Where in the body do you suppose we want to shift the curve to the right periodically? Do we want to do it here in the lungs, or would we want to do it here in the tissue spaces? I want you to think about that for a second. Where in the body do we want to favor shifting the curve to the right? Lungs or tissue spaces? Where do you want to favor unloading? Tissue spaces, right? Tissue spaces. All right, so with that in mind, let's think about some of the things we might expect to find in the tissue spaces, especially actively metabolizing tissues. What do you think about temperature? Temperature in actively metabolic tissue is going to be higher or lower than, say, in the alveolar space? Yeah, if you said higher, you'd be right. So an increase in temperature is one of the things that shifts the curve to the right. And when you want to understand mechanistically what's going on here, these are factors that alter the shape of the hemoglobin. And by altering the shape of the hemoglobin, we change its affinity for oxygen. So temperature causes the hemoglobin to relax a little bit, and it favors the unloading of oxygen. Okay, what else do we find in actively metabolizing tissues? What do you think about the pH? Now here we got to pause for a second to think about this. In the pH, what happens? Well, to understand this phenomenon, we have to understand that if you take CO2 and you dissolve that in water, that converts to this guy. Bicarbonate. Oops, I'm sorry, actually. Let me fix that. I went one step too far. Erase. That converts to this guy. This is not bicarbonate yet. Oh, for crying out loud. Okay. Carbonic acid. So you dissolve CO2 in water and it will spontaneously convert to carbonic acid. Now carbonic acid, the name acid here, tells us what happens next. Carbonic acid will break down and give us hydrogen ion, so that's what makes it an arsenous acid, and finally bicarbonate ion. And it's this guy that causes the problem. Or in this case, it's a good thing. Right? If we liberate hydrogen ion, well, that's an increase in acid, and so that actually causes the pH to go down. Declining pH. More acidic. So actively metabolizing tissues produce more CO2, which in a roundabout way then converts to more carbonic acid, the liberation of more hydrogen ion, and a decline in pH. A declining pH shifts the curve to the right, and thereby favoring the delivery of more oxygen to this metabolically active tissue. So a decrease in pH shifts the curve to the right. And now that you understand that, it should make sense that in addition to that, increasing CO2 levels also shift the curve to the right. If you increase CO2 levels, well, that does a couple of things. One, it forces its way onto the hemoglobin and changes the hemoglobin's affinity for oxygen that way by forming carbaminohemoglobin, but also it forms more hydrogen ion. So to go over these three things, an increase in temperature shifts the curve to the right. decreasing pH shifts the curve to the right, and increasing carbon dioxide levels all shift the curve to the right. And these are all the results of metabolically active tissues. And that's what we want to have happen in the tissue spaces. All right, let's compare that to what happens now in the lungs. Well, or what we want to have happen in the lungs. The lung spaces are being bathed with outside air, which is usually not the same temperature as the air in the body, or the air is usually below body temperature. So that tends to make the lungs cooler than the blood. So that, a decrease in temperature, is going to shift the curve to the left. And if we look at what happens there, if we shift this curve leftward, okay, and you look at this, okay, say we were at a PO2 of 40. Well, if we came up here, now that would remain bound to quite a bit more oxygen. So shifting the curve left favors oxygenation. Okay, shifting the curve left favors oxygenation. We'll say it one more time. Shifting the curve to the left favors oxygenation. So this is something we want to encourage in the lungs. Okay. So a decrease in temperature shifts the curve to the left, and then just the opposite of everything we said before. Another factor that will shift the curve left would be an increase in pH. An increase in pH. And a decrease in carbon dioxide levels. And that's exactly what we have in the lungs. When we vent carbon dioxide off in the lungs, we get a decrease in pH. I'm sorry, an increase in pH and a decrease in carbon dioxide levels. So we shift the curve left naturally in the lungs to favor oxygenation. I don't know why, when I learned this in physiology the first time, this was a complete mystery to me, but it's really pretty straightforward. Metabolically active tissues produce conditions that shift the curve right to favor unloading. The lungs produce a set of environmental and metabolic conditions that shift the curve to the left, favoring loading. It's that simple. Or, I won't say simple, but that's straightforward. Okay, I mentioned the fact that hemoglobin can be a reserve. I'll talk about this guy, BPG, in just a second here. Okay, so this is kind of showing what I was mentioning. If our standard curve were the pink line right here, and we had decreasing body temperatures, well, look at that. That shifts the curve powerfully to the left, holding on to the oxygen. This one down here is showing the effect of decreasing carbon dioxide levels, which would also accompany an increase in pH. Right. And that would also shift the curve to the left, favoring oxygenation in the lungs. All right, so we were just discussing the factors that shift the hemoglobin association curve either to the right, favoring unloading, or to the left, favoring loading. And we said, as this graph here shows us again, just to reiterate, that factors such as decreasing temperature, increasing pH, and decreasing CO2 levels all shift the curve to the left. And that is what we want to favor in the lungs. And if we flip that around, decreasing pH, increasing CO2 levels, and increasing temperature all shift the curve to the right, favoring unloading. Now there's an interesting thing that occurs with the CO2 and the pH. And it can be summed up in what's collectively called the Bohr effect. We've already described it, actually. As a result of increasing CO2 levels trying to force their way into the hemoglobin, and the decreasing pH and what that does to the structure of the hemoglobin actually becomes less fond of binding to hemoglobin. So the hemoglobin becomes less fond of binding to oxygen is what I'm trying to say. So the Bohr effect says that, hey, look, as PCO2 levels go up, the result of increased CO2, and as pH goes down, the result of increased hydrogen ion, that the hemoglobin to oxygen bond weakens, and so we unload more oxygen. That's exactly what we want to do. And so this actually is a shift of the curve that we see to the right. That's what the Bohr effect is showing us. That's the rightward shift of the curve. Oxygenation. Well, there's some things to consider about oxygenation. Inadequate O2 delivery leads the tissues to take on a bluish appearance, and that's called cyanosis. We can become hypoxic. Hypoxia means not enough oxygen in the blood. Well, the most likely reason to not have enough oxygen in the blood is to not have enough oxygen carrying capacity in the blood, which means we don't have either enough hemoglobin or we don't have enough red blood cells. So that would be anemic hypoxia. You can also get impaired flow, and so that's ischemic hypoxia. That would be the leading cause of strokes and heart attacks when you have a blocked blood vessel. Histotoxic hypoxia, this is what would happen with the case of metabolic poisonings, things like ricin toxin and detrodotoxin. These are things that bind actually to cytochromes, make it impossible to use oxygen. Hypoxemic hypoxia, that simply means abnormal ventilation. Pulmonary disease, we'll talk about that at the end of this chapter. Carbon monoxide poisoning. Let me pause here for a second and expound on this just a bit. Carbon monoxide, C bound to O instead of CO2. Remember, we made mention of the fact that carbon dioxide does not bind to the heme center of the hemoglobin, where oxygen binds. So I think somebody had asked in class, is it possible for hemoglobin to bind to both? And I said, well, in physiological situations, no. But in a laboratory, you could. You could elevate the levels of carbon dioxide and oxygen to the point where you could get hemoglobin to bind to both. Carbon monoxide is different than carbon dioxide in that carbon monoxide actually does bind to the heme ring in the place of oxygen. And it does so, and check this out, 200 times greater affinity than oxygen. Now, I can't really explain why that is, but carbon monoxide binds to the heme center much more tightly than does oxygen, which means if you come in contact with even minute amounts of carbon monoxide, it gets into your hemoglobin and effectively causes anemic hypoxia. It removes those hemoglobin from the pool that can actually bind to oxygen and deliver it to your tissues. And because it binds with such a greater affinity, the only way to get that out of there is to force oxygen in and replace it. Well, that's very hard to do under normal PO2 concentration. So the treatment for carbon monoxide poisoning is to take somebody and put them in a hyperbaric chamber where we can elevate the pressure of oxygen in that chamber and slowly but surely force the carbon monoxide out of their hemoglobin. Okay, so we've talked a great deal about how we transport oxygen around the body. Let's talk a little bit about how we transport carbon dioxide around the body. As I made mention to you, unlike oxygen, where the vast majority of oxygen, 98% of the oxygen, is transported by hemoglobin, and only about 1.5% is transported in the plasma, we have an appreciable amount of carbon dioxide dissolved in the plasma, maybe up to 10%. Then we have about 20% actually bound to hemoglobin. So that only makes up maybe 30% maximally of all of our carbon dioxide. Where's the rest of it? Well, 70% or so is transported in the form of bicarbonate ion. This is partially why our PCO2 levels never seem to rise very high, because we convert it from carbon dioxide into bicarbonate. Now that's a protective mechanism, because if we didn't do that, that would cause the pH to go plummeting as CO2 levels rise. And this is going to help us understand that a little bit. And I think I made mention of this on another chart. When we dissolve carbon dioxide in water, a fairly slow reaction forms carbonic acid. Carbonic acid then breaks down about 3% of the time into hydrogen ion and bicarbonate ion. So this by itself would be fairly slow. But there's an enzyme in the body. Actually, the fastest enzyme known in the human body is carbonic anhydrase. And carbonic anhydrase, and I'll just put Ca here, Carbonic anhydrase catalyzes this reaction and speeds it up 1,000-fold. So now what would ordinarily be a fairly slow reaction actually takes place in red blood cells very, very quickly, because that's where you have a lot of carbonic anhydrase. So as carbon dioxide diffuses into the blood from cells and gets into red blood cells, the red blood cells just bang zoom convert it into carbonic acid, which breaks down to hydrogen ion and bicarbonate. The bicarbonate diffuses back out into the blood, and then hydrogen ion is snapped up by hemoglobin or other proteins or other buffers in the blood. To compensate for that flux of bicarbonate out of the red blood cells, chloride ion in the blood just shifts into the red blood cells. That's all the chloride shift is. Here's a diagram showing what I was talking about. Here's CO2 diffusing into the interstitial fluid. It's going to be picked up by the capillaries, and that's what this pink area represents, the capillary with the plasma in it and the red blood cells. So you get a little bit of CO2 diffusing directly in and stays dissolved. So that's our maybe 5 to 10%. We get some CO2 diffusing in and going through this relatively slow reaction to carbonic acid. That one's not catalyzed in the plasma, but in the red blood cells it is catalyzed and happens very, very rapidly to generate our bicarbonate and hydrogen ion. So here's hydrogen ion binding to hemoglobin, and instead of doing creating reduced hemoglobin, pardon me. And there's the bicarbonate that we've produced. So this is the travel form of carbon dioxide, which now is free to diffuse back out into the plasma and be carried that way. And there's the counterbalancing chloride ion shift coming in to counteract the electrostatic repulsion we would get with the bicarbonate fluxing out. Well, in the lung epithelium, we kind of run the process in reverse. Now we take that bicarbonate back into the cells. Carbonic anhydrase now catalyzes the conversion of it back into carbonic acid and then the breakdown into CO2 and water, and now we vent the CO2 off in the lung spaces. So where the Bohr effect speaks to the reduced affinity of hemoglobin for oxygen in the presence of large amounts of CO2 and hydrogen ion, we also have an effect called the Haldane effect, which says that, look, when I have a high concentration of CO2, not only do we give off more oxygen, which would be the Bohr effect, but that also increases the uptake of carbon dioxide. And so that encourages the uptake of carbon dioxide in the tissues. And it's pretty much just the fact that when carbon dioxide and hydrogen ion are available, it reduces the hemoglobin, and that reduced hemoglobin has a higher affinity for carbon dioxide. So the way I try to remember this is that the Bohr effect has to do with CO2 and hydrogen ion, i.e. lower pH, and its effect on red blood cells and hemoglobin in that it gives off more oxygen. And the Haldane effect is looking at it from the perspective of CO2. The Haldane effect says pretty much the same thing about increased CO2 and hydrogen ion, but it speaks to the effect of carbaminohemoglobin actually having a higher affinity to bind more carbon dioxide. Alright, sometimes I spend a fair amount of time talking about the buffer system in the blood. Our blood is at least triple buffered, meaning that it has a phosphate buffer, an amino acid buffer, but most importantly a carbonic acid buffer system. So for this I'm going to bounce back and look at this diagram where they already have the relevant things written to ease my life a little bit and yours. So let's erase what we have here. Now in chemistry we go into the functioning of buffers quite a bit, and it's not my goal to revisit all of that. But I do want to mention a few things. What a buffer is. A buffer is something that resists change. What a pH buffer is the set of chemicals that when you add an acid to the system binds up the free hydrogen ion and prevents the pH from changing. When you add a base to the system, it either liberates hydrogen ion to neutralize the incoming base and convert it to water, or it actually binds to and removes the hydroxide ion from solution, and thereby also preventing the pH from changing. So that's really what a buffer does. It's two sets of chemicals that in one condition can act like a base and neutralize an acid, or in another condition can act like an acid and neutralize a base. So when you add acid or base to a buffered solution, you get very little or no change in pH within the buffering capacity region of that chemical. Like any buffer, if you add too much or stress the system too much, you'll eventually overwhelm the buffer and the pH will change. So let's see how that happens. It all depends on carbon dioxide. So here we go. If we add hydrogen ion to this system, and remember that would be the functionary in an acid. Well, what we have to have is we have to have a way of neutralizing this acid. If you have free hydrogen ion in solution, then the pH goes down. So what happens when we add an acid? It binds to the available bicarbonate ion. Bicarbonate converts to carbonic acid, and carbonic acid is broken down to CO2 and water. Now, assuming that we're able to ventilate normally, our ventilation rate can go up a little bit. We can vent off a little more CO2 and the pH normalizes, and we're fine as long as we have an available supply of bicarbonate. We can neutralize incoming acid. Well, remember, a buffer has to work if you add an acid or a base. So we've covered how the system operates if you bring in an acid. What happens if we bring in a base? Well, a base, you might remember, the Arrhenius definition of a base is something that gives off hydroxide ion. Now, if hydroxide ion comes into the system, it encounters the available hydrogen ion, binds to that, and is neutralized as it becomes water. So that's how we can neutralize the incoming hydrogen ion. Now, of course, if that were the whole story, that would snap up our available hydrogen ion, and we would rapidly start to have an increase in pH. So if that occurs, we compensate for that by breaking down more carbonic acid. So if we did use up the hydrogen to neutralize the incoming hydroxide ion, more of this would break down to replace that hydrogen ion. And of course that would give us bicarbonate. So one of the things we say about buffers is that buffers are usually a weak acid or a weak acid or a weak base and the salt of their conjugate base. So carbonic acid is a weak acid. So H2CO3, and I'll just put WA for weak acid. Its conjugate base is this guy, what's left over. When I give off a hydrogen ion, I wind up generating a negative ion. That's a base. This is the Bronsted-Lowry definition of a base because it can be a proton acceptor. That's a base. So if I take HCO3 here, my definition of a buffer is a weak acid, and the salt, so to make this a salt, I'll add a counterbalancing sodium ion in here. And that is the base. I'll just put conjugate here, or just con base. So to have a buffered solution, well, with the sodium there, it's no longer negative. Okay. NaHCO3 is sodium bicarbonate. So you want to make a buffer. You take some carbonic acid, like seltzer water, and you can add some sodium bicarbonate to it, and voila, you've got yourself a buffer system. And this is the buffer system that exists in the blood. Okay. So if you have acid come into the system, bicarbonate binds to it, generates carbonic acid, which can be broken down into CO2 and water. If you have base coming into the system, acid can bind to it, neutralize it, convert that into water, and then a little bit of carbonic acid can break down and regenerate our supply of hydrogen ion and bicarbonate. And you can see carbon dioxide is the main functionary in this buffer system. Okay, if we're bringing in excess acid and converting or neutralizing that acid by converting bicarbonate into carbonic acid, we have to get rid of that eventually by venting off more CO2 in the lungs. The respiratory rate will increase. If, on the other hand, we're bringing in base and we're breaking down carbonic acid to generate hydrogen to neutralize that to water, then we have to retain more CO2. We slow down our ventilation rate to retain more CO2 to go ahead and give us more carbonic acid to allow for that. So that's the bicarbonate carbonic acid buffering system in a nutshell. All right. So there's a few things to talk about in the chapter still, and I think I'm going to let you read a fair amount of this on your own because I don't ask too many questions about it. Really what I sum up here is that carbon dioxide, dissolved carbon dioxide levels are sensed in the hypothalamus and the coronary sinus, not coronary sinus, in the carotid sinus. And actually that's what stimulates most of your breathing reactions. It's elevated levels of CO2. You're relatively insensitive to changes in PO2 until the PO2 in the systemic arterial circulation falls below 60, which would only happen under dire circumstances. Breathing is controlled by the medulla oblongata of the brainstem and the pons. Oops, I didn't mean to do that. Normal breathing is called eupnea. And 12 to 15 breaths per minute is a normal resting breathing rate. The phrenic nerve is what is responsible for most of quiet breathing because it innervates the diaphragm with the supporting role played by the intercostal muscles. Let's take a look at a picture here. So we're looking at a sagittal section of the brain, looking mostly at the midbrain and brainstem. Here's the pons, there's the medulla. There's an area down in the brainstem called the ventral respiratory group and the dorsal respiratory group. And my understanding is fairly simplistic on how this works, but the ventral respiratory group generates rhythms. In other words, that sets the pace for the breathing. That's your respiratory rate is set there. The dorsal respiratory group is involved in alternating either inhibition or excitation of the respiratory muscles. And then somehow, in a way that I don't think is particularly well understood, the pontine respiratory center, so up in the pons here, receives sensory information about blood oxygenation levels, CO2 levels, body temperature, and even emotion, and regulates both the rhythm generating center and the dorsal respiratory group switching between inhalation and exhalation. And guys, really all I expect you to know is that there are these structures called the VRG and DRG that are in the medulla, and they're partially influenced by the pontine respiratory center. But in a nutshell, the brainstem is what regulates your respiratory rate. So you don't need to worry about the hypotheses about how this works. And then this is just summing up what I said, that it's really arterial PCO2 levels that are the strongest influence in your respiratory rate. Most of that is due to changes in pH. Okay, we know that as pH goes up, as PCO2 goes up, pH decreases, and the brain and the hypothalamus and the medulla respond to that by increasing respiratory rate. Some of that is also controlled by the actual monitoring of the CO2 levels in the blood, and so they give it a 70-30 split, and I'm never going to ask you to quote those numbers. Hyperventilation, as we mentioned before, will vent off too much CO2. So we talked about this in the context of perfusion ventilation coupling. So if you hyperventilate, you give off too much CO2, and the blood actually becomes alkaline. So not enough CO2 is called hypocapnia. The blood becomes alkaline, and you start to have things like vasoconstriction to the brain, and so you get cerebral ischemia, and that causes all sorts of things like muscle impairment, tingling, dizziness, fainting. Apnea is the term apnea. Apnea simply means not breathing. All right, skip that. All right. The Herring-Brewer reflex is a hyperinflation reflex that inhibits the muscles and the respiratory center from breathing in once you've stretched the lungs to a certain point. So it's a protective mechanism is really all you need to know about that. The Herring-Brewer reflex prevents hyperinflation of the lungs to where you actually damage them. Okay. I want to get to the slides to talk a little bit about disease. I guess this is the right place for this. One of the results that you can have when you are at very high altitudes is that the air becomes thinner. The pressures are less, and actually the concentration of oxygen decreases as well. So they mention here that travel above 2,400 meters can lead to this thing called acute mountain sickness, and it's just a cadre of symptoms that are related to basically hypoxia, headaches, shortness of breath, nausea, and dizziness. As a result of extreme vasodilation in response to hypoxia, you can actually wind up having the capillaries become too leaky and you get edema, which could be lethal. Acclimatization is the idea that if you slowly progress at these increasing heights, that your body will go through some physiological changes to help protect yourself. Your ventilation rate will increase slowly. Your basal ventilation rate will increase. You'll also, I think it gives you a few other things here. Your kidneys will respond to the hypoxia and they'll secrete more EPO, which we know will drive blood cell synthesis up. And you also create a chemical called 2,3-BPG. 2,3-bisphosphoglycerate. I think it may be diphosphoglycerate in your book, but 2,3-BPG. This is a chemical that's produced as a result of glycolysis, which we know is the anaerobic stage of energy generation. But for our purposes, what we want to know is that 2,3-BPG can be deposited in red blood cells and actually shift the hemoglobin dissociation curve strongly to the right. Okay, so what does shifting the curve to the right favor? See if you remember. Shifting the dissociation curve to the right favors unloading. So it's something we want to do in our tissues. So you can imagine the advantage here. If you're hypoxic, 2,3-BPG, elevated 2,3-BPG levels make it easier to deliver oxygen to your tissues. An interesting side note, if blood is donated and taken out of the body, the BPG levels in the red blood cells decline sharply after about 6 weeks. And that is actually the limit to how long you can store blood in a blood bank. And it's the effect of the degradation of the 2,3-BPG. So if BPG levels shift the curve to the right, and that favors deoxygenation, well, what happens when it's gone? Well, if it's gone, the curve shifts heavily to the left, and then you oxygenate the blood, but you don't give up the oxygen. So if you received a transfusion from blood that was too old and the BPG levels were low, you would effectively give the person ischemia. The brain and the heart would suffer from deoxygenation, low oxygenation levels, and you'd have a heart attack or a stroke. So blood can only be stored for about 6 weeks because of that. All right, a few things about homeostatic imbalances. Chronic obstructive pulmonary disease, COPD, something that affects almost 1 in 5 people as they age, exemplified by chronic bronchitis and emphysema, as it says there. So bronchitis, we know, is an inflammation in the bronchi of the respiratory tract, and emphysema is a pulmonary condition that's categorized by a loss of respiratory membrane. The alveoli become greatly expanded, whether it's due to fibrosis of the lungs for unknown reasons or more likely environmental impact, chiefly cigarette smoking, will actually cause the alveoli to become greatly expanded, much more fibrotic, and you lose respiratory surface. As a result, you become barrel-chested because we're trying to increase the ventilation to compensate for the decreased diffusion rates within the lungs. So you wind up having labored breathing and this air hunger idea because of reduced air exchange. And you wind up getting hypoventilation. So now we're not ventilating properly, and we talked about this when we talked about ventilation perfusion coupling too. If you don't ventilate properly, then what do you build up in the alveolar space? What's not swept away? Carbon dioxide. So this leads to a buildup of carbon dioxide chronically. And as we just mentioned a minute ago, if you build up carbon dioxide in the blood, that means that your pH goes down because the carbonic acid converts to carbon dioxide is converted to carbonic acid, which then lowers your pH. So you wind up getting what's called a respiratory acidosis. So this winds up putting a lot of stress on the lungs. Well, no, it's caused by stress on the lungs. I'm doing poorly here. Sorry, guys. A respiratory acidosis caused by hypoventilation, which is a result of something like emphysema or COPD, puts a lot of stress on the kidneys, because as we'll talk about in the renal chapter, the kidneys are constantly trying to void off hydrogen ion if it's excess in the blood. All right. All right. Anything else? So asthma is an obstructive disorder, as is COPD, that's reversible. Asthma is characterized by extensive bronchoconstriction, which is usually caused by some sort of inflammatory response, which is talking about here. It's fairly easily controlled in an acute outbreak of asthma, simply controlled by giving a powerful bronchodilator, which is usually ephedra or adrenaline, epinephrine. Okay. I'm going to talk about tuberculosis. Guys, I'd suggest you read over the lung cancer part. I'm never going to ask you questions about adenocarcinomas, squamous cell or small cell. Just obviously lung cancers. This is interesting. Lung cancers are the leading cause of cancer deaths in the United States. And I don't know how you estimate this, but 90% of all cases of lung cancer are caused by, or at least are synonymous with, people that have smoked cigarettes. All right. And that's it. Okay. That ends the respiratory chapter, guys. I think the next one I have to do is the reproductive chapter. So thanks for slogging through it with me, and I'll try to get better at this as I go.